Hello, hello! Welcome to 5.3 number 1. Once again, that is 5.3 problem number 1. Now, this problem involves a situation where you're on top of a 100-meter building. And you're up there and something bad happens to you. What happens to you is you fall. You fall. Now, fortunately, way down at the bottom, you got some firefighters. And they're down there with their little hats. And they have a way to save you, and they're going to save you with a big old net. And here's the net. Now, the question is, how far is this net going to stretch if you land in it? Now, what we know is that the mechanical energy, sorry, wrong way I'm writing that, mechanical energy at the beginning, the initial mechanical energy, should be equal to the mechanical energy at the end. Now, this does not always happen. Obviously, potential energy isn't going to transfer completely into kinetic energy and then into elastic potential energy. There's going to be loss. There's going to be wind resistance and heat from the rubber stretching and stuff like that. But let's just say it really did work like that. Your gravitational potential turns to kinetic, but then your kinetic energy, when you hit the net, turns to elastic potential as the net stretches and brings you to a stop. Let's find out what our situation is here. So, initially you're at the top with gravitational, I don't know what's wrong with me today. Gravitational potential energy, and that's initially, is going to equal elastic potential at the end. The formula for gravitational potential energy is mgh. And the formula for elastic potential is 1/2 kx squared. K is the spring constant, and x is how far it's stretching. Actually, guess, now that I think about it, you're stretching downward, that x should be a y. Shouldn't it? All right, so let's figure out what y will be. Now, if we start out here, my mass is 108.9 kg. Gravity Earthlings is 9.8 times 100. And that's going to equal 1/2. Now, k, we give you a k value here of 20,000, which is pretty darn strong. Of course, you're expecting it to stop you after falling 100 meters. So it's going to be pretty strong. And of course, we got y squared. So if I multiply all this together, my mass times 9.8 gives me my weight, the force of gravity. Force times distance, the distance I'm falling is 100 meters, is my potential energy. When I multiply this together, I get an amount of energy of let's see, what do I have here? I have, so I have 106,722 joules, which is strangely not as many calories as you would think. So 106,722 joules is going to equal the joules that are going to be stored up in the net when I come to an end. 1/2 of 20,000 is 10,000 y squared. If I divide both sides by 10,000, that's fairly easy to do. You don't even need a calculator for that. I simply move the decimal point 1, 2, 3, 4, and I get 10.67 is equal to y squared. But we don't want y squared, we want y. So we take the square root of both sides, and we end up with 3.3 meters is equal to y. So the net is going to stretch 3.3 meters, which means I'm probably not going to make it anyway. Because unless these firefighters are 20 feet tall, there is no way they're going to hold a net so they can stretch 3.3 meters without me hitting the pavement pretty hard. So, looks like there's not a lot of hope for me. Now, you guys are probably lighter than me. If you're lighter than me, your mass is going to be less, your weight will be less, and then your weight times 100 will mean you have less potential energy. Less potential energy going in means that that net will not stretch anywhere near it. Well, it won't stretch as much. So expect to get a number that's smaller than that. And who knows? Maybe the net will stop you before you hit the pavement. It just didn't work for me. So there you have it, 5.3, number 1. Here we go.